When Pokémon Red and Blue released, over 30 million aspiring trainers set out on their Pokémon journey. The first obstacle is a fight against your rival where you secure an easy victory. Nobody would ever lose the tutorial fight, right? Well, I can prove with mathematical precision that millions of players suffered a crushing defeat in the first minutes of the games they had so anxiously awaited, and there was nothing they could have done about it. The inherent randomness of Pokémon battles means you can never be sure what happens when you choose a move, so how can we calculate our chance of losing a battle purely due to bad luck? Or even better, avoid that by finding the optimal strategy. Let's start the battle. Naturally, we choose Bulbasaur to get preemptive revenge on how the Charmander line has monopolized attention for the last 30 years. Each monster has one attack, Tackle or Scratch, to deal damage to the opponent. If Charmander doesn't have any health points left, we win. Further, both parties can use Growl to lower the opponent's attack. While the damage dealing attacks get us over the finish line, these status moves enable us to develop strategies. You may think this is simple, just weaken your opponent when hit hard, but since Charmander has its own status move to weaken your attacks, this approach could be your downfall. We use the mechanics of the first generation of Pokémon games, which is also why the sprites look so funny. This means we don't need to think about many features like abilities or held items, because they didn't exist back then. I list some of the technical details in the description in case you are interested. When I say that we develop a strategy, that means we need to find the optimal move to use for each state of the battle. A state is the condition that the monsters can be in when the game asks us to select a move. In our case, that's just the monster's HP and whether their stats changed. In the end, our algorithm should keep track of the state that we are in and tell us which move is the best choice. This is a bit tricky, since the game doesn't tell us the exact HP value of the opponent, but more on that later. I'd like to stress that the algorithm won't just use some kind of artificial intelligence to make an educated guess. We are going to use rigorous mathematics to calculate exactly how our chances of winning lie with each option. The first step to do so is to formalize how each choice we make will play out. Let's consider what happens if we use Tackle. There are three main checks the game needs to go through. We are going to represent them in a graph, starting from the state we are in. First, the game checks whether the move misses. If so, we are done for this turn, otherwise we continue. If the attack hits, the game now checks for a critical hit. Again, we split the path in our graph. Finally, the game deals damage to Charmander. To make it a bit less predictable, the damage dealt includes a random factor. In our graph, we could represent this by creating a new path for every possible outcome. However, it is easier if we just note that there are several possible values. We might say that Charmander's HP are no longer a definite value, but a superposition of several options. After all of this, the game will check whether Charmander has sustained so much damage that it faints. Of course, it is impossible for Bulbasaur to win on the first turn, but we'll split our path for completeness. This graph now shows us exactly what happens if we let Bulbasaur attack with Tackle. If we use Growl instead, we'll get a very similar graph. The game checks whether the move hits, and Charmander's attack can still get any lower in the first place. If both tests pass, Charmander's attack decreases. We also need to consider Charmander's options. The game performs essentially the same checks as before, so we can just reuse our graph from Bulbasaur's turn and swap the two monsters. The only difference is that we don't know beforehand which move Charmander will use. From the player's perspective, this is randomly determined when Charmander starts its turn, so let's add a node to connect the graphs. Finally, we need to bring both monsters in order. In our case, we know Charmander is always faster. For simplicity, let's say Bulbasaur uses Tackle, so we attach our Tackle graph to the end of Charmander's turn. After both monsters have taken their turn, the game asks the user for their next input. We have now moved from the initial state of the battle over to one of those we find at the end of our graph. This is quite interesting. We know that after the first turn, the game can only be in one of these states. In principle, we could now play out the graph that we found for each child state and find all states we can reach after 2 turns and so on. However, we can do this in a more efficient way. Like many players, we'll simplify this and only use tackle for now, keeping the option to use growl in the back of our heads. The graph we have constructed can be considered a kind of machine the game uses to decide what to do when we click the attack. We feed our current state in at the top, and out comes a list of result states with their probabilities. Note that most of what we draw as one state is actually a superposition of several possible HP values, so this list already contains quite a lot of states. The problem is that if we feed a different state into our machine, the states that come out at the end are completely different from those we got from the last state, which makes it a bit difficult to formalize the process. We apply a simple trick that lets us translate this machine into mathematics. While the graph gives us a list of all reachable states and their probabilities, we can add all unreachable states to the end with 0 probability. That doesn't change anything for when we are testing a single state, but if we compare outputs for 2 different states, all that changes now are the probabilities associated with the states in the list, but the list of states itself is always the same. In a way, this means that our machine doesn't even output states. It only gives us the probabilities that we end up in a certain state after the next turn. Each entry corresponds to a certain state, so we can just drop them from the picture. As you may have guessed, this list of probabilities is a vector. Naturally, we would like the input to our machine to be a vector as well, so we apply the same trick. Rather than saying that we give it a single state, we can just rephrase it and say that we enter a vector of probabilities for all states, but all entries are 0 except the one we are using, which has a 1. The remaining question is how we can reformulate our machine itself in this mathematical picture. Since we are already using vectors, it comes as no surprise that it is going to become a matrix. Just as for the vectors, each row and column of the matrix corresponds to a state, in the same order as for the vectors. Letting the game play out moves will then be a simple multiplication of our input vector with the matrix. But how do we construct it? Well, we already have the answer. If we put a state through our graph, we get its result vector. Considering how matrix multiplication works, putting in a vector with only one non-zero entry means to ignore all columns of the matrix except one and just copy it. So this column must be the vector we get as an output from the graph. To construct the matrix, we simply need to pass each possible state through the graph and put the vector we get into the matrix as a column. We also add the states where we win or lose the battles, which always lead back to themselves. At this point, we have successfully reduced the fun, colorful game of Pokémon to a dull grid of numbers. How does this help us finding our chance to win? Intuitively, it should be easiest to do so for states where the battle is almost over, so let's go straight to the extreme. We look at a state where both monsters are down to 1 HP and their stats have already been lowered as much as possible. The next turn can play out in 3 ways. Charmander moves first. If it uses Scratch, it wins. But its AI routine is equally likely to choose Growl, in which case nothing happens, because we said Bulbasaur's attack is already at the minimum. If so, Bulbasaur can use Tackle and win, unless it rolls the 5% chance to miss, in which case we return to the same state. The matrix of these 3 outcomes looks like this. Calculating the win rate is actually easy. From our state, there is a 47.5% chance that Bulbasaur wins, and a 50% chance to lose. If neither happens, we simply move back to where we started. By consequence, we can say that the chance to win here, call it x1, is 1 times the chance to move to the win state, plus 0 times the chance of going to the loss state. We also add about 0.025 times x1 itself, for when the game loops back to the same state. While we could simply solve this for x1 to get our answer, let's find a more general way. We can simplify the equation by subtracting x1 and clearing out the right side. While our goal is to calculate x1, we can also add the matrix rows of the other two states along with corresponding variables. We add x2, the chance to win in the win state, and x3, the chance to win in the loss state. These are trivially 1 and 0, which we can directly encode in the right hand side of the system of equations. As before, we obtain the chance of winning x1 by solving this system of equations for it. Obviously, this is more work than just solving a single equation, so how is it helpful? To see that, let's use that system and get back to our matrix representation. The first step is to factor out the unknowns x1 through 3. We do so by rephrasing it as a matrix vector product. Next, we undo the subtraction we did on one of the diagonal entries earlier. By transposing, we get back to our original transition matrix. But that is only a fraction of the entire matrix. What would happen if we performed the transformation on the matrix for the whole battle? Well, we obtain a system of equations that gives us the win chance for any accessible state. We simply need to solve it and look at the entry of the battle's initial state to find that, as long as Bulbasaur always uses tackle, our win chance is only 45%? For many players, just spamming the attack is the go-to strategy for this battle. But in the first rival fight, this spells demise for more than half of them. Surely, we can do much better by playing a bit more strategically. To do better, we need to choose between tackle and growl depending on the situation. But there's a problem. The whole point is that we can set up a matrix which we interpret as a set of equations to solve. But this matrix depends on our strategy. If we take the start of a battle, when we choose our first move, we basically choose between two different rows that we can put into the matrix, one for tackle and one for growl. These two rows give us equations to calculate the win rate for both options. But to evaluate these equations, we need to know the win rate on every child state, for which we would need to make the same choice between the two moves for every child. If we cannot even construct our matrix, how would we ever solve it? It's not actually that difficult. We start with a matrix that is so small we can solve it and work our way up from there. Let's return to the example state where both monsters are at 1 HP. In theory, we have a choice between tackle and growl, but choosing the latter is always a bad idea since we cannot win this way. So we do know which matrix were to put for this state. Now, we add another state to the matrix that can only lead to the state for which we know the optimal move choice, or an AND state. For example, let's say Bulbasaur is at 2 HP, while Charmander is still at only 1. Again, we test out both options and go with the better choice. In this way, we can move through all possible states. In the end, we don't even need to solve the system that we get, because we already found all win rates and move selections while constructing it. This is our optimal strategy. For each of the 17,024 theoretically accessible states, our algorithm can tell us the move to pick along with our probability to win. We find that, with mathematical precision and the optimal strategy, we can beat blue in just shy of 75% of battles. These aren't even good odds, but remember that over 30 million of these games were sold. While we don't know exactly how many young trainers chose Bulbasaur, it is very likely that several million of them lost their very first Pokémon battle. And the actual loss rate is going to be higher since these kids played far from optimally. Of course, the chance to win depends on the starter you choose, and Bulbasaur really is an outlier here. If you choose Charmander and play optimally, your chance to beat Squirtle is a staggering 98.7%, and you get the same result when fighting Bulbasaur with Squirtle. Unfortunately, we just proved Bulbasaur is actually the worst starter, at least for the first battle. One thing to note is that these probabilities don't necessarily apply to your own rival fight. Your monster stats are a bit randomized, so your Bulbasaur might be a bit stronger or weaker than the one I chose, which has average stats. Now that we have found the optimal strategy, we should assess whether it is useful in the first place. As you remember, the amount of damage the monsters deal has a small degree of randomness. While we can always see exactly how many HP Bulbasaur has, we don't get a lot of information about Charmander's HP except if its health bar's color changes. It would thus be possible that we are in a superposition of a few states, some of which would need us to use Tackle and others Growl. In practice, this only happens if the choice hardly matters, since the states are still very similar. If we really want to play perfectly, we can even determine Charmander's HP exactly by counting the number of pixels in the health bar, so this isn't a big issue. The true problem is that our optimal strategy is entirely impractical. While it gives us the best move for each situation, keeping track of the current state is incredibly tedious for a human player. Since the optimal strategy is impractical, you may wonder how much better it is than strategies you can use yourself. We have already seen that if you only use Tackle, Bulbasaur loses the majority of battles. If we Growl once and then start using Tackle, we already win in 57.5% of attempts. Using Growl twice raises our chances again to 68.2%. Using Growl a third time harms our win rate. Indeed, it plummets to 55.4%. But this is deceiving. After the fourth Growl, our win rate skyrockets to 74.2%, hardly distinguishable from the optimal outcome. The dip occurs because the Game Boy can only use integers, not rational numbers. Due to this rounding, Charmander deals the same damage after the second and third Growl, but you wasted a valuable turn in the latter case. However, you should start attacking now, since the damage output cannot get any lower and you'd only end up wasting turns. In conclusion, we find that for the average Bulbasaur, you can simply use Growl 4 times at the start of the battle and get essentially the same results as for the optimal strategy. And there you have it, an algorithm to transform a Pokémon battle into a matrix from which we can find optimal strategies by using some linear algebra. While the truly best strategy is impractical, it allows us to prove that a simple stand-in is essentially as good as it gets. You might wonder how far we can push it, and the answer is that I wonder too. At this point, my implementation doesn't yet include many of the major game mechanics, so its applicability to battles that come later in the games is more restricted by that than the necessary computational effort. Though I do believe that with a lot of optimization and a bit of patience, this kind of algorithm can definitely beat a Nuzlocke. But for now, let's be content that we have found the optimal way for Bulbasaur the underdog to take down an overrated Charmander.